Hi all. The following is a presentation of my Asiacrypt 2023 paper on black box knowledge sound commit and prove snarks. My name is Helge Lippmaa. I come from Estonia. Let us first remember basic principles of non-interactive zero-knowledge arguments. An argument usually has a prover and a verifier, where both prover and verifier have access to a public statement X, and the prover additionally knows some private witness W. Knowing this witness W, the prover aims to convince the verifier that some property holds about X. For example, X is a satisfiable circuit. To convince verifier, prover sends a short argument by to the verifier. More precisely, an ASIC has to satisfy a number of properties. First of all, it has to be complete. Then it has to be sound. Then it has to be zero knowledge. But it can also satisfy a number of additional properties. For example, if the argument is short, then the ASIC is usually called a snark, a succinct non-interactive argument. Moreover, if the argument satisfies knowledge soundness, that means that honest verifier does not accept if P does not know the witness, then the snark is called a snark. There's a very famous impossibility result about snarks by Gentry and Wicks. Based on this result, every snark paper ever claims that their paper uses non-falsifiable assumptions or random oracle model due to the impossibility result of Gentry-Wicks. So what does Gentry-Wicks say? Basically, it balances four different desirable properties of snarks. First of all, the snarks should be adaptively sound. Second, they should be succinct. Third, they should be for hard languages. And fourth, they should be based on falsifiable assumptions. Gentry-Wicks said, or their paper said, that you cannot achieve all four properties at the same time. An important question is to understand if this result is tight. It is known to be tight in three aspects. So in each aspect, you know that three of the properties can be achieved, but one cannot. For example, a very classical result says that you can achieve the other three properties, but the argument is going to be non-succinct. Similarly, you can achieve other three properties, but the argument is going to be based on non-falsifiable assumptions. Until lately, it was completely unclear if Gentry-Wicks is also tight in the fourth aspect. That is, can it be proven, or can one construct a construction that achieves the last three properties but satisfies a weaker version of soundness, by which people usually mean non-adaptive soundness. There has been some progress in this field in the last few years. First of all, in Asiacrypt 2021, we showed that Gentry-Wicks is indeed tight. That is, we can achieve the last three properties, but the soundness is going to be non-adaptive. Moreover, our construct was a snark, which means that it didn't satisfy knowledge soundness. In this year, Campanelli and others had a paper where they showed that this not achieving knowledge soundness was actually the best possible, in the sense that one cannot achieve the last three properties and at the same time have a non-adaptively sound snark. Their paper had also a positive result, which said that you can achieve basically the same properties that we achieved in the Asiacrypt 21 paper, but it was for a much, much smaller complexity class. Now, this might seem weird, why they proved this result, but the real reason behind that is that our Asiacrypt 21 paper has a flaw. Our construction there doesn't work. This was known to me, unfortunately, already 2 years ago, and in this paper we show why this is indeed the case. To try to correct this paper, we define a new soundness notion, semi-adaptive soundness, and we prove that one can achieve the last three properties, but the cost will be that the snark will be semi-adaptively sound snark. That is, it will be knowledge sound. This is, however, a new notion of adaptivity. And we still don't know after this work if one can construct non-adaptively snark that satisfies the last three properties. Campanelli, etc. showed that it cannot be snark, but maybe it can be a snark. We don't know. So we have a new construction and we leave an open question. The interesting thing is that this is also a question whether one can separate snarks and snarks. Let us now recall what is adaptive soundness. Here I'm going to talk about adaptive commit and prove snarks, in which case the trusted third party first sends a CRS to the prover. The CRS can contain a commitment key, and it usually does. The prover, after that, constructs a statement and an argument and sends those two values to the verifier. In most of the cases, the argument contains a commitment to the witness. Because here X and Y are sent at the same time, there's no fundamental difference whether the commitment is a part of the statement or the argument. And thus we can think of it as being a part of the statement. And thus we usually get the commitment proof snark or snark. The next classical adaptiveness notion is that of non-adaptive snarks. In those snarks, the prover first sends the statement to the verifier. The verifier replies with a CRS, and the prover sends the argument to the verifier. Since the statement is sent before the CRS, the statement cannot contain a commitment to the witness, and thus the snark cannot be commit and prove. Let us next explain what is black box extraction. Black box extraction is very well understood in the case of interactive protocols. Let me give an example of Sigma protocols. In a soundness proof of a Sigma protocol, the prover sends the first message to the extractor. Extractor then chooses a random second message and obtains a third message from the prover. After that, the extractor rewinds the prover and sends a new random second message, C prime, that is different from C to the prover. And after that, prover sends another third message to the verifier or the extractor. And the requirement is that if both transcripts of the protocol were accepting, then the extractor can extract the witness. And indeed, it's very well known how to do it in the case of any secure Sigma protocol. It is much less understood how to achieve black box extractability in the case of NISIC. You can imagine that the prover starts by sending a statement to the extractor. Extractor sends CRS and maybe some other information to the prover. Prover replies with an argument. Then the extractor rewinds the prover and sends a different CRS to the prover and gets back another convincing argument. Intuitively, we would like now the extractor to be able to output the witness. Unfortunately, this is not so easy. Let us see more precisely what happens in the case of non-adaptive snarks. So, as said, in the new non-adaptive snarks, first the statement is sent, then the CRS, and then the argument. Intuitively, it can be shown quite easily that extraction is going to be impossible here. So what's the intuition? The intuition is that the prover can use a different witness in each rewind. And there's not enough rounds to build a contradiction because there are no public parameters sent before X is sent. The prover cannot commit to the witness, and thus the prover is free of using a different witness in different cases or different rewindings. I must stress here that this is only an intuition. This is definitely not the proof. And Gentry-Wicks and the paper of Campanelli prove impossibility by using also the fact that the proof is succinct. Nevertheless, it is an intuition that we are going to build on. One more thing here is that in our Asiacrypt 21 paper, I would say that our paper is mostly correct, but we made a crucial mistake at some point that is not so easy to see, where we just assumed the prover uses the same W. This assumption is not true because we did not enforce it somehow, and we also didn't use the fact that the prover uses different witnesses to build some kind of a contradiction. To solve this solution, we somehow need to add more rounds. So welcome to our second contribution, which is the definition of a new soundness notion, which we call semi-adaptive soundness for commit and proof snarks. In this soundness notion, the trusted third party first sends a commitment key to the prover. The prover replies with a statement and with a commitment to the witness. Then the trusted third party sends CRS to the prover, and the prover sends an argument to the verifier. The main reason here why we have this new adaptive notion is that we have more rounds. So we have more rewinding points for the black box extraction. In particular, we send the commitment key before the statement of the commitment. This means that commitment can be a part of the statement. Let us give now a very brief intuition to the knowledge soundness proof that we have. In this proof, the extractor first sends the commitment key to the prover. The prover replies with a statement and a commitment to the witness. The extractor now does the following many times. It rewinds the prover, sends to the prover a new CRS, and gets a new argument. More precisely, there's going to be one rewinding per each wire of the circuit. Each time the CRS is reprogrammed, and more precisely, the CRS is somewhere extractable. This means that during the ith rewinding, we can extract from this argument the neighborhood of the ith gate. The next step in the knowledge soundness proof is going to be as follows. Namely, if the prover used two inconsistent witnesses, we extract two inconsistent wire values. But those wire values both have been committed to by using the same commitment. And our insight here is that the commitment is going to be a vector commitment. So from different opening of a single wire, we can construct a contradiction. We construct an efficient, semi-adaptively sound commitment proof snark Punic. That is really practical. Other contributions of the paper are breaking the old paper, defining the new knowledge soundness notion, building several new tools like a new vector commitment scheme, and also the new proof technique. Getting a practical construction is a major hassle and requires several new insights and tools. Also, it is possible to use the classical construction of Killian in this case, but this is going to be utterly impractical and nobody is probably ever going to implement it, especially because it uses PCP. Unfortunately, we don't have time to discuss this construction almost at all. Still, a very high-level overview of Punic is as follows. First, the trusted third party sends a commitment key of the vector commitment scheme to the prover. Prover replies with a statement and a vector commitment to the witness. The trusted third party now sends to the prover the CRS, and crucially, the CRS contains the commitment key of a functional somewhere extractable commitment. Finally, the prover sends to the verifier the argument, where now the argument contains a functional somewhere extractable commitment to the witness and to the openings of the vector commitment scheme. For this to work, we have to design a new vector commitment scheme that basically is FSC friendly. I will not be able to define it here. So the very high level idea is that we will have a vector commitment to the vector of wire values, and we will have a somewhere extractable commitment to the vector of wire values and to the vector of vector commitment openings. And the intuition is that if there does not exist a witness satisfying all gates, then there exist two gates, I and J, such that pi used different values of some wire that is in the common neighborhood of both gates, at least for one wire. After that, in the knowledge soundness proof, we use the somewhere extractable commitment to obtain two contradictory wire values together with corresponding vector commitment openings. And then we use the values, contradictory values together with openings to break the position binding property of the vector commitment scheme. Here is a bit of example that what you need is two gates that share a wire that might have contradictory values. We use several tools here, and not all of them are well known. The first one is functional somewhere extractable commitment that can be based on DDH. The second one is bilateral subspace quasi-adaptive NISIC that can be based on Esker MDH. The third one is a new FSC-friendly vector commitment that we propose in the current paper, but which is partially based on existing schemes. And the final component we need is a relatively new assumption that was proposed by us in 2021. The main security theorem of our paper states that if those three tools are secure and this fourth assumption holds, then our construction is semi-adaptively computationally F-special sound. And after that, we can use standard tools to obtain knowledge soundness from special soundness. That's it. Thank you very much for listening, and please read the paper.